Hey guys, so my cat and I here are hanging out at my kitchen table, and since I can't come to class tomorrow because of my jury duty, I figured that the two of us would collaborate here and do a little bit of a walkthrough for the first few pages of Chapter 5 of the course packet, focusing on the quantification of uncertainty. Boy, you're feisty today. So Markov here is just going to hang on my lap and make yourself a cup of tea and open up the course packet, and let's get started. Okay, so here we are in Chapter 5 of the course packet, which, as the title says, is about the quantification of uncertainty. The idea of uncertainty played a pretty critical role in the way we defined statistical modeling back in the very beginning of the course. We defined it as the structured quantification of uncertainty. And we focused a whole lot on the structured part of that definition. Things like regression equations, maybe involving transformations or polynomial terms, grouping variables, analyses of variance, so a lot about structure. But we've talked about uncertainty only a very little bit, and we're about to fix that omission right now. So if we think about uncertainty, there are really three crucial questions that we can ask. The first one is, how confident are we in our estimate of an effect size? And by an effect size, I could mean a number of different things. So if you're looking at a 2x2 contingency table, an effect size could be measured by a relative risk or an odds ratio. If you're looking at a difference between two group means, the effect size might be how much bigger one group mean is than the other. So that might be quantified using the coefficient on a dummy variable, for example. In an ordinary linear regression model or in a power law regression model, it might mean the slope or the power of the equation that we're fitting. So however we're measuring an effect that quantifies a relationship between two variables, that effect is going to be estimated subject to error. And that error could take a number of different forms. The most obvious would be sampling error. If we took a different sample from a wider population, we would likely get a different data set, a different set of points to fit equations to, and therefore a slightly different estimate of the effect size, be it a relative risk or an odds ratio or a slope in a regression model. The question is, how much different could it have been, and how confident are we in the answer that we've got for our particular data set? A second big question about our uncertainty is how confident we are in our forecast. Now, we've touched on that one a little bit in the context of naive prediction intervals, but we ignored something important, namely that we have uncertainty about the systematic part of the model, like the parameters and the model specification itself. And it stands to reason that that uncertainty about the parameters in a regression model ought to somehow percolate forward into additional uncertainty about the future observable quantity that we're trying to forecast, above and beyond the contribution of a future residual. Our naive prediction intervals didn't take that uncertainty into account, and we're about to fix that here in this chapter. And then finally, there's a question about whether an association could plausibly be down to random variation. And so as an example here, if you consider this contingency table that we saw a few chapters ago from the PrediMed study, this quantified the relationship between whether somebody was a present or a former smoker. That's the columns of the table, and the rows of the table indicated whether or not that person had a cardiovascular event, so like a heart attack or a stroke or death due to cardiac causes over the course of the study. So this table right here has a particular association in it, and we calculated the relative risk. The natural question is, what if we taken a different sample of people? After all, we don't have the whole population, whether it's, whatever that means, whether it's the population of Spain, where this study was conducted, or the population of the wider world. We've only got a sample. A big sample, yes, but not everyone. And if we had taken a different random sample of folks, is it plausible that that relative risk wasn't 1.94, but in fact was 1, or it just totally went away? And so if the association could plausibly be due to chance, that's something we ought to know when interpreting a contingency table like that. Now, we use the phrase statistical inference to describe uncertainty quantification in all of these contexts, and there are many ways to approach inference. We're going to learn a particular approach in this chapter called a resampling-based approach. Okay? And so the fundamental idea of uncertainty quantification is the following equivalence, which I've written down here on the bottom of the page. It's that we can be confident in our estimates if and only if those estimates would be stable under the influence of chance. And so again, the easiest way to think about what chance would entail here would be to think about a scenario involving random sampling. You have a wider population, you take a sample of folks from that population and try to understand some feature of a wider relationship here, like the slope between two variables in the population or a relative risk between two categorical variables in that population. On the basis of that sample, we want to provide an estimate of something about the population. So what if we'd had a different sample? You can imagine taking 1 or 2 or 10 or a hypothetically very large number of samples, and the fundamental question is how stable would our answer be under all of those different possible samples, of which we only have 1. And the notion here is that if our answer is unstable across those different samples, then there's no reason to trust it for our particular sample. If, on the other hand, you get pretty much the same answer every different sample from the population, and every time there's some kind of chance occurrence that affects your data, well, then that stability means that you can have a lot more confidence in the estimates that you have for your particular data set. So that thought experiment of what's happening in all of these parallel universes, all these roads not traveled, when our sample was different or when the random forces influencing our data set were different, is a really important thought experiment to have in the back of your mind when you think about uncertainty quantification and statistical models. Okay. And so there's a lot of sources of instability. Let me just jump straight to the idea of random sampling that we mentioned. Okay, so here's an example in this picture right here. I like this example because it's very intuitive. Imagine you go to a lake and you go fishing. And let's say you go fishing every day for a year. And every day of that year of fishing, you catch 15 fish from this lake. And you're in a statistics class. You decide to take a little bit of data about each fish. So what you do is you measure the volume of the fish, and that's here on the x-axis. And you also weigh the fish, and here's the weight of the fish in grams on the y-axis here. Okay, and so these ghost gray points, the light gray dots here in the background, you've got to imagine that's the whole population of fish in the entire lake. Now, obviously, on the basis of your fishing trip, you're not going to know what that is, but let's pretend that somehow, some way, somebody's taken a survey of the entire lake, and we know exactly in the background what these volume and fish of every fish in the lake are. So that's the gray dots right here. On your fishing trip, let's say day 1, you go to catch these 15 blue fish right here. So these guys right here, all these little blue dots, those are the fish that you caught on your first day of fishing. So now you fit a straight line by ordinary least squares that captures the weight versus volume relationship, and you get this blue least squares fit. Great. So that's your best guess for the relationship between weight and volume for the fish in the lake. Now you go day 2, and let's say you pick these red fish right here. So that's 15 fish on day 2. 1 fish, 2 fish, red fish, 4 fish here. And that's the straight line that you estimate. You can see this red line right here. And because you caught a different sample of 15 fish, you have a different estimated red line. That's pretty intuitive. And more to the point, neither is exactly equal to the right answer. So the right answer for the whole lake is this dotted black line right here. Okay, so they're both different from each other, and they are different from the truth, and that's sampling error and sampling variability. Okay, so you go back on day 3 and you catch these 15 kind of lime green fish right here, and you get this line, this green line, and then finally on day 4 you go back and catch another sample of 15 fish. You get these light blue fish right there, 15 of them, and you get this line. Okay, so you're beginning to get a sense of how variable of an answer you can get for the relationship between weight and volume on the basis of a sample of size 15 fish. Okay, well, 4 fishing days is enough to give you some kind of idea of what variability that you might experience. It's a lot better to do this by computer, and so I simulated 2,500 days of fishing, which is a lot of fishing. That's like many years of going fishing every day. And what you're seeing here, they're not colored now, they're just every single one is a very, very thin light gray line. But what you're seeing here, every single line is a different least squares line fit to a different sample of 15 fish. And we refer to this dispersion here, this distribution of fitted lines about the truth, which is the dotted red line here, as the sampling distribution of the least squares estimator. And if we were to tally up all of the slopes and all of the intercepts associated with these 2,500 lines fit to 2,500 different samples, it would look like these 2 histograms right here. Here's the 2,500 intercepts that you got, beta naught, and here's the 2,500 slopes that you got. And these histograms are, you think of them as approximations to the sampling distribution of the least squares estimator. And by sampling distribution, it's sort of just what it says on the cover there. It's the distribution of results that you get under repeated sampling from the wider population. Okay, so every single data point that went into these histograms corresponded to a single sample, a single least squares fit of 15 fish. And if you think about schematically what's happening here, I've written it for 1,000 samples here, but there's a very, very large number possible here. You've got a wider population here. You're taking many, many, many different samples. For each of those samples, you're forming some estimator. And so that estimator, concretely in our example, would be the least squares estimator of the regression relationship between weight and volume. In many other examples, it could be a different estimator, like a sample mean, or a difference of medians, or group means, for example. Generically, we'll call that estimator theta hat, trying to estimate some population-level quantity theta. So these are all the parallel universes that we're imagining. For every parallel universe, you form your estimator, and then at the end, you imagine pooling them all into a histogram. And so this histogram right here corresponds intuitively to these same histograms right here for these 2,500 different fishing trips. Okay? And that's the sampling distribution. How would we quantify something about that sampling distribution? Well, probably the most natural thing, let me page back here, is to say, well, how variable were the estimates? And that's very intuitive. If the estimates were always very close to the same value, so this histogram were highly peaked around 50 or so, well, you can say that there's not a lot of uncertainty associated with that estimator because we get the same answer every time. The answer is stable under random sampling. Similarly, if this slope estimate here were always peaked around the truth, maybe 4.25, then you could say that because the answer was stable under random sampling, a very, very similar answer every time, then we can trust our estimate. And the degree to which you have dispersion around the center of this distribution is giving you some notion of how stable or unstable your answer is under random variation. And so we would summarize that dispersion using the standard deviation of these distributions. And we have a special term for the standard deviation of the sampling distribution. That's called the standard error. And that's very intuitive. It's the average error you make when you use the estimate from your sample to estimate the population truth. Okay? So that's how our thought experiment works. We imagine taking repeated samples in a limit, a hypothetically infinite number of samples from the population, and seeing how stable our estimator is under each of those samples. And that sounds very, very impractical if you bother to think about it, right? We started off by saying we have a sample from a population. We want to know how much we can trust that answer from that sample. And so what this line of thought seems to be suggesting is that the only way to say how certain we are for our answers on the basis of that sample is to go collect a whole bunch more samples, maybe 1,000, maybe even 10,000 new samples. So not only does that seem stupid on the face of it, right? Just to take an example, if you went and collected 100 different samples of 15 more fish, you wouldn't have one sample of 15 fish. You would have one sample of 1,500 fish, and you'd be wanting to know about what the uncertainty associated with a sample of size 1,500 would be. So that's one obvious reason why we would never do this in practice, because if we were to collect those samples, we would have more data and we would need to answer a different question. The other reason is that it's obviously impractical for the vast majority of all problems. Collecting data can sometimes be expensive, especially if it involves surveys or experiments, and we don't want to actually put this thought experiment of all of these parallel universes into practice just for the sake of quantifying uncertainty. So how do we do this, right? How do we somehow get access to these parallel universes that we're imagining being essential to the quantification of uncertainty without ever actually taking more samples? Well, there's a couple ways of doing this. And the one that we're going to learn here is called the resampling-based approach. And that has a very straightforward assumption under the hood. The assumption is that we treat the sample as if it's a stand-in for the wider population, and therefore, instead of taking samples from the population, we repeatedly take samples from our sample. Okay, so that's called resampling. Another name for it is the Bootstrap, and we're going to talk about that here in a second. The other way that we can proceed is called parametric probability modeling. If you took your first stats course and talked about things like the normal distribution or the t-distribution, that was all parametric probability modeling. And that's a fine way of proceeding as well. It involves making mathematical assumptions about how regular or irregular the forces of randomness are that influence your data, and then using deduction to reason about those mathematical consequences. We're not going to talk about that now. We'll talk about it in a later chapter. We're going to talk about the resampling approach. Okay? So at the core of this resampling approach is a very, very simple idea. We cannot feasibly take repeated samples from the wider population in order to see how our answer from one sample to the next changes. But what we can do is take repeated samples from the sample itself and apply our estimator again every time to these new resampled samples from our original sample. And so the idea here is just to pretend that you do have the whole population, except to use your original sample as a stand-in for the population. And that seems odd on the face of it. One thing that's obviously puzzling here is the following. Our goal is to answer the question, how much does our answer change from one sample of size n, let's say concretely n is 15, so from one sample of size 15 to another sample of size 15, to another, to another, to another. And if we're going to take repeated samples of size 15 from our original sample of size 15, it seems as though we would have a problem that we would always get the same sample over and over again, like 15 members of the population, so your sample can only have those 15 members. And that points to a subtle point about bootstrapping, that when you resample from your original sample, you have to do the sampling with replacement, or catch and release to invoke the fishing analogy. So when you catch one fish for your sample of size 15, you throw that fish back into this hypothetical lake representing the wider population, and therefore it could actually be caught again because you're sampling with replacement. And that means that one sample of size 15 from your original sample will have some particular pattern of ties and omissions, and that pattern of ties and omissions will be different from one resample to the next. And it's that unique pattern of ties and omissions that gives this process variability, and the whole thought is that that kind of variability is going to mimic or approximate the variability that you would get if you could take repeated samples from the actual population. So this process is called bootstrapping. It's kind of a metaphor, like we can't sample from the wider population, so just pull yourself up by your own bootstraps. And so let's summarize what bootstrapping looks like. So, and this is going to be directly parallel with the earlier schematic that we were walking through. So instead of the population up here, we've got our original sample. And what we're going to do is we're going to use the power of modern computers to replicate the following process over and over again. We take one resample, that's also called a bootstrapped sample, from our original sample. So in our fishing example, there's 15 fish up here in our original sample, and we take a sample with replacement of 15 fish. So there's not going to be 15 unique fish. There'll be some ties and omissions compared to the original sample, but we don't care about that. Let's form our estimator, and then let's do it again. Take another unique sample with replacement from your original sample, form your estimator, and do it again and again and again. So here's an example of 1,000 times. So we've got 1,000 different estimators all applied to their own unique bootstrap samplers, and now we pool those and we call what results is the bootstrap sampling distribution. And so this idea is very, very simple to apply using the power of modern computers. We do a Monte Carlo simulation, which is to use a computer to approximate this random process right here of over and over and over again, resampling from our original sample and forming the estimator afresh each time for each notional sample. Okay, so this is not free lunch, right? The quality of this process and how well that this schematic is going to replicate this schematic up here, which is what we'd like to do, take repeated samples from the wider population, is going to depend mainly on one thing. We've got the population up here in this thing that we'd like to do, and in this thing that we actually do under bootstrapping, we've got the original sample up here as a stand-in for the population. So it makes sense that the accuracy of this process is going to be really limited by the extent to which your original sample is a good approximation to what the wider population looks like. And you're not going to get very accurate answers in approximating your standard errors and your sampling distributions if the original sample is biased or otherwise impoverished as an approximation to the wider population. Okay? And so again, if we formed our original sampling distribution and quantified our uncertainty using the standard error, we do the same thing with this now practical recipe as opposed to the impractical thing we couldn't do before. We've got our bootstrap sampling distribution, and we take the standard error of this distribution right here, just its standard deviation. Okay, so that's the idea behind bootstrapping. And let's now talk about confidence intervals. All right, this picture right here is a nice picture, and I encourage you to spend some time with this picture as it's narrated through in the course packet here. on page 113. This picture is just designed to give you an idea of how well bootstrapping works in practice. So up here, we've got the actual sampling distributions corresponding to samples of 15 fish, 50 fish, and 100 fish. And then down below, you're seeing 4 examples of the sampling distributions you get. Here's one sampling distribution from bootstrapping one sample, bootstrapping another sample, bootstrapping a third sample, and so forth. And so spend some time with this picture and kind of get a sense of how well bootstrapping works in practice. I'm going to move on to the idea of confidence intervals. Okay, so intuitively, a confidence interval is just a range of plausible values for some truth about the world, like a population level parameter. Concretely, the true slope for all the fish between weight and volume in our lake. And a confidence interval, a range of plausible values, also comes with an associated confidence level between 0 and 100% that conveys the precision with which the data allowed you to estimate the underlying population parameter. Okay. So how do you form a confidence interval? Well, using bootstrapping, there are 2 ways. Okay, so one we call the basic standard error method, and it looks like this. We've got our estimate from our original sample, that's theta hat. So, for the least squares estimate, if we're trying to estimate the population slope, this would be the estimated slope from our sample. We've also got the standard error calculated by bootstrapping. So we do this whole bootstrapping procedure using a Monte Carlo simulation. We calculate the standard error, that's sigma hat right here, and now we go symmetrically to either side of theta hat some multiple t star, and t star here is called the critical value. And so typical choices here would be things like t star equals 1, t star equals 2, and usually those correspond to roughly something like 65 to 70% confidence intervals for t star equals 1, and about a 95% confidence interval for t star equals 2. We're not going to talk too much about why that is. There's a little footnote on it over here. But that's the basic standard error method. Just go symmetrically to either side of our estimate for our actual sample using the standard error estimated by bootstrapping. The second way is called the coverage method. Okay, and this is going to look, this has a very simple recipe. We've got our bootstrap sampling distribution right here, and to be specific, this is the answer that we get for our sampling distribution of the slope for the fish example before, when we take one sample of size 30 and we bootstrap that sample in order to approximate the sampling distribution. So now this, we could use this to form a range of plausible values just by forming a coverage interval of these numbers right here. So chop off 10% down here and 10% up here, and this blue shaded area here now corresponds to a bootstrapped 80% confidence interval. And this is going to be a little bit different than the standard error method right here, because you can see this has to be symmetric about your estimate, your least squares estimate, whereas this need not be. It can be skewed to one side or the other depending on the shape of the sampling distribution. So is one way better than the other? Not as a general rule. I should mention that both of these are somewhat simple, naive ways to get standard errors and confidence intervals from bootstrapping, and there are much more mathematically sophisticated and frankly mathematically daunting ways of getting bootstrap standard errors. If you are interested in seeing some of those, I give you a little link in one of the footnotes here. It's in footnote 7. This article right here will walk you through some of the more sophisticated ways of doing it. You're absolutely not responsible for that. We're going to stick with one of the 2 ways, either the basic standard error method here or the coverage interval method right here. Okay? All right, let's close this off by talking about one tricky question that often comes up in the context of sampling distributions, and that does, what does confidence mean? Okay? And so to understand what the confidence means in a confidence interval, we need this idea called the frequentist coverage principle. And here's the principle, right? This is sort of a truth in advertising property about confidence intervals. It's the following. Imagine you were to go out and analyze one data set after another for the rest of your life. So maybe you were to, again, let's go back to the fishing example. To go one day after another, fish and catch 15 fish the rest of your life, and every time you went fishing, you claimed an 80% confidence interval for the slope between weight and volume. The frequentist coverage principle says that in the limit, the frequency with which your confidence interval contains the truth should be the stated number. So here, 80%. So in the long run application of the procedure for generating your confidence intervals, the frequency with which that confidence interval covers the truth should be 80%. So that's why it's called coverage. Does it cover the truth or not? And frequentist, because it's a claim about the long run limiting frequency with which your stated confidence interval actually contains the true value. Okay? And so to give you an example of bootstrapping in action here, we've got this picture over here on the right. And the idea of this picture is to illustrate that the bootstrap confidence intervals we get, and these use the coverage method, but you could also use the standard error method, do approximately satisfy the frequentist coverage property. Okay, so here's what happened. We took 100 different samples of size 30 from that population of fish, that lake, back from figure 5.2 here. And for every single sample, we did 1,000 bootstrap resamples from that sample to form a bootstrap sampling distribution. And then we use that bootstrap sampling distribution to compute a confidence interval. Okay? So the true value for the population is right here, this vertical line. Every single one of these little dots or crosses and gray bars right here represents 1,000 different regressions, right? Because there's one sample, and then we bootstrap that sample 1,000 times to compute the bootstrap sampling distribution of our estimator. And these gray bars here represent the 80% confidence interval generated using the bootstrap coverage method. So the X here was the estimate we got from that sample. And if it's a red X, it indicates that this confidence interval did not actually contain the true value. On the other hand, if we have a blue dot, so here the second data set, we did 1,000 bootstrap resamples from that second real sample, and notice that this confidence interval does cover the truth right here at 4.24. So it gets a blue circle. Miss, miss, make, miss, make, make. So after 100 of these real samples, bootstrapping every single one, so just count that up, that's 100 real samples, and then for every real sample, we did 1,000 bootstrap resamples and fitting a regression. So it took 100,000 regressions in order to make this figure, 5.8. But, computers are pretty darn fast, and so this didn't take all that long in the end. And what we get to do is now count up how many of these dots are blue versus red. And so if you actually count this up, you're going to find that you've got 17 red crosses and 83 blue dots, meaning that the empirical coverage fraction of these confidence intervals is 83%. And so the stated fraction was 80%. So not bad, right? The claim is approximately true. We were aiming to cover the truth 80% of the time. We actually covered the truth 83% of the time. So we did well there. Okay, so that about wraps things up for the first little bit of the chapter here. We've covered the idea of a sampling distribution, the idea of using bootstrapping to approximate that sampling distribution and get access to all of those notional parallel universes in which we had different samples. And now we've talked about how to form a range of plausible values, i.e. a confidence interval, using that bootstrap sampling distribution. And that allows us to address our first fundamental question about uncertainty, which is how certain are we about an effect size? In this case, the slope of a least squares regression line.